well, I'm just going to get started. So, as you all know, weather conditions, no final CSG meeting, so that's a little bit disappointing. But I spent like a day or two writing this talk, so I would be annoyed if I didn't get to give it. So, anyways, today I'm going to be talking about BCKW Combinator calculus, and really I'm going to be examining Haskell Curry's PhD thesis. And don't worry if neither of those things means anything to you. Hopefully it will. So, a bit of history first. The year is 1930. Haskell Curry is a PhD student at the University of Göttingen. He's studying under the legendary mathematician David Hilbert, and he's working with another legendary mathematician, Paul Bernays. And 6 years prior, this guy named Moses Schonfinkel publishes a paper called On the Building Blocks of Mathematical Logic. I'm going to move my camera over here so I'm looking at it. So yeah, Moses Schonfinkel, he writes a paper called On the Building Blocks of Mathematical Logic, and he was attempting to formalize the description of mathematical propositions. So like 2 is even, or all natural numbers that aren't 0 or greater than 0, like any mathematical proposition you can think of. But he failed to go into enough detail. He didn't write rigorously enough. And so, if I recall correctly, Schonfinkel didn't really pursue this area for a while. But Hilbert, Curry's PhD advisor, he was famous for striving to describe the foundations of mathematics at the deepest level, and try to work out any kinks or inconsistencies that were in the current math system at the time. And Bernays is familiar with Schonfinkel's work already, and Curry has already written a small preliminary paper expanding on Schonfinkel's discoveries. So Curry had been interested in this for a while, and he had been writing this thesis. And so the setting is perfect to finally formalize the construction of mathematical propositions. And just a side note, so I said Hilbert, he strove to describe everything perfectly and work out any kinks. But in 1931, there was this other mathematician named Kurt Gödel who kind of curtailed that effort with an incompleteness theorem that he published, which I'll talk about in a little bit. So here are the people. We got Curry, Hilbert, Bernays, and then on the bottom we have Alonzo Church, the inventor of lambda calculus. We have Alan Turing, who invented Turing machines and computing, really. Schonfinkel, and then Kurt Gödel. So first I'm going to go over Schonfinkel's discoveries. Is my stream going? Sorry, I just want to make sure it's up. Yeah. So Schonfinkel proposed a set of combinators to represent theorems. And combinators are basically just functions. They take in some amount of arguments and they evaluate to something. That's it. In a normal math and even programming, you'd have a function. If it takes 3 variables, it might be f of x, y, z, and it's got those commas and it's got the parentheses. But in combinator calculus and in lambda calculus and in functional programming as a whole, you're going to see something like f, x, y, z all together in a row, which really means fx, y, and then z. And so it's a left associative. That's what it means, is that kind of the things on the left stick to each other first. Okay? And Schonfinkel's combinators are these: B, C, K, and W. These might look ridiculous to you. I mean, you got some capital letters, you got some X, Y's, and Z's, and all it really looks like is that they're transforming the order and the existence of some of these variables. But believe it or not, this is a valid way to represent all of mathematics. The system is Turing complete, so it's a very interesting proposition in my opinion, and one that goes overlooked a lot of the times. So I'll give a brief rundown. B is like composition. So if we have two functions f of g and we want to apply g to x, we've got g of x, and then we put f outside. We say we've got f of g of x, right? That's what the B combinator is doing. The C combinator will switch the second and third arguments that it gets. The K combinator is called the constancy combinator, constancy function, because it just deletes its second argument. And W, which actually I don't think Sean Finkel had W in his system. I think Curry came up with that one. I have to double check on that one, but pretty sure Curry came up with W, where it just doubles its second argument. And so I'll just give a little example. Curry, in his thesis, very early on, proposes that the sequence BCC, those three combinators, applied to X, which could be anything. It could be another combinator. I'll say it could even be the plus function, or is prime, or is even, or some function, or anything. That's what X could be. He proposes that BCC is the identity function. So if you do BCCX, you just get X out of it. And so let's derive this. So we've got BCCX, and from our B rule, B says XYZ, or BXYZ equals X applied to Y applied to Z. And so in this example right here, C is our X, C is our Y, and X is our Z. A little confusing, sorry about that. But so we do X of Y of Z. Okay, C of X. That's good. But we ran into an issue. If you go back, C expects 3 arguments. But right here, this C only has 1 argument, and this C only has 1 argument, because that entire parenthesized expression counts as 1 argument. That didn't go the way I had hoped. How are we supposed to progress from here? And we need a little aside. So we need to introduce a concept called currying. Yes, it is named after Haskell Curry. And basically what the idea of currying says is that if you have a function, let's say it's got 3 arguments. Let's say, for example, we've got void main down here. It's got 2 arguments. It's got an int argc. It's got an int pointer or an int pointer array argv. And then its return type is void. And void isn't really a return type, but I'm not going to get into that. I'm just going to say that this function over here has this type. And these arrows, don't exactly worry about what they mean, but you can just trust that the thing on the right is going to be the output type, and the whatever comes before that is the input types. So this says that main has type int to int pointer to void. And if we wanted to curry main, which we can't do in C, but you'd have to use a functional programming language typically, what currying would entail is, instead of giving it the 2 arguments that it asks for, I only give it 1 argument. So for this example, let's imagine that I give it argc. It's not going to yell at me for giving the wrong number of arguments. What it's going to do is it's going to actually give me a function back that is just int pointer to void. So it's kind of consumed that first integer, and it's giving me a function to the rest of the stuff. And if I take that resulting function and I give it an int pointer, it would run main, or it would do something, right? So the idea of currying is basically just giving arguments one at a time instead of all at once. And the thing you get out of it is a function without the type that you just gave it as an input type. So a little confusing. I attached this this passage right here from the textbook that Dr. Hamlin mentioned in the lecture he gave this semester. I'm not going to read through it, but I encourage you to because it's a very good explanation. And so back to our combinator example, we can use currying to think about what the result would be like if we gave BCCX 2 more arguments. And in this case, I'm going to call them blank 1 and blank 2, just because I don't want to call them Y and Z because they're not really there. But anyways, blank 1 and blank 2. And we could have blanks 3 through 1,000,000 or 1,000,000,000 or whatever. But I'm just concerned about 1 and 2 right now. So CCX is what we stopped at last time. And we're going to just put those blank arguments after it. And now we have this C. Oh, look, it's got 1 argument, that's CX. It's got a second argument, that's blank 1. And it's got a third argument, blank 2. So we can use the C rule, which says that CXYZ equals XZY. And so here, this is our X, this is our Y, this is our Z. Oh, I guess, yeah, you can't see my pointer. Yeah, so CX is our X, blank 1 is our Y, blank 2 is our Z. And so applying the C rule, we get CX, blank 2, blank 1. And now at this point, we can actually discard the parentheses here. And I'm not going to get into why. Go read Curry's thesis. He'll tell you why we can get rid of the parentheses, but we can. And again, we can use the C rule, which says that CXYZ equals XZY. So here, X is our X, blank 2 is our Y, and blank 1 is our Z. So let's swap those second 2 arguments, and we get X, blank 1, blank 2, which is the order that those arguments should be in. So if I plugged in B or C or K or W or any combination of those into blank 1 and blank 2, I would get just X again, plus those arguments. So this is the identity function. BCCX is IX. So that's cool. Great job, Haskell Curry. Thank you for that. But why does any of this matter? I mean, we haven't done anything useful with it yet. And we will in a little bit. But so Sean Finkel came up with these rules in 1924, or at least that's when he published the paper. But he actually didn't write a true proof that the combinators could be used to do anything interesting. Curry actually wrote a pretty scathing review in his thesis, which I found pretty surprising. I wasn't expecting this. He says, because Sean Finkel has in no way shown how the introduction of the other fundamental concepts is to be avoided, and because he cannot define them from the others, he has not justified his claim. In fact, he has achieved only a new and inconvenient notation. So I thought that was a little funny, but and if my PhD advisor were David Hilbert, I'd probably be pretty dissatisfied with that too. Hilbert was trying to formalize the description of mathematics as a whole, so that we could ensure that it's not consistent, it didn't have any, or that it's not inconsistent, it didn't have any paradoxes or anything. So a loosey-goosey definition of mathematics is definitely not what Hilbert had in mind. And I encourage you to go read about Hilbert's program. Basically, in the year 1900, Hilbert posted a list of 10 big questions that he wanted to solve about mathematics, and like logic questions. And for example, one of them was, is mathematics decidable? Which means, is there any algorithm that can be used to show that every true statement is true? And there were 9 other problems, but I'll get more into that later. But if you're interested in the history of this, strongly suggest you go look at the Veritasium video about Hilbert and his program. So I'm not going to walk you through all of Curry's thesis for a few reasons. Number one, it's a PhD thesis. It's not Harry Potter. It's not that interesting to most people. It's very interesting to me. It is deceptively simple towards the beginning. I read through part 1 and I was like, oh man, this is going great. I'm loving it. I'm understanding everything. And then I got to part 2 and he opened up part 2 with like 8 more brand new conventions and nothing made sense. So if you're going to read it slow, make sure you're internalizing. and you should read it here. This link right here contains these slides, and my transcription of his thesis, and another thing that I'll talk about later. But so instead, I'm just going to broadly summarize his strategy for proving that combinators are Turing complete. Wink, wink. And just a fun fact: Turing machines weren't actually proposed until 1936. Turing completeness just means that a system can perform any decidable computation. So, Chapter 1. Most of sections A and B basically are just explaining the need for why do we need a formalization of mathematics. And they lay out some philosophical groundwork, which I found really interesting, that kind of sets the stage for the rest of the thesis. So just a couple big concepts. A good system of mathematics has very few axioms, and axioms are just statements that we assume to be true, but they should not forfeit any generality at all. A good system of mathematics eliminates all paradoxes that arise from the pre-logic that exists underneath mathematics. And pre-logic is kind of like intuition. It's like things that don't seem right, but we can't explain why or anything like that. And so the example that he gave was Russell's paradox, which says, if I have some function f and it takes in an argument which is also a function, and it equals the the opposite of the function applied to itself. So think of Boolean negation, right? Well, what if you plug f into itself? Then you have ff equals the negation of ff. That's an issue that comes out of pre-logic, and Curry aimed to not have any inconsistencies like those. And then the third one that I found very interesting was that contradictory concepts, like the statement that a property and its negation are true, they're not inherently meaningless, and you can't disregard them right away. So again, he goes into much more detail. Read the thesis if you're interested. Section C evaluates Schonfinkel's approach, and it proposes new axioms to build off of. Axioms, that's a strict description. And Section D proposes and proves theorems regarding the equality of sentences of combinators. So he'll say, if you have a sentence that is, or a sequence that is made up of these kinds of combinators in this order, that will reduce down to something else. And Chapter 2 is where it gets rougher. So he starts off the chapter with a bold claim that anything that you can derive in the standard frame of mathematics at the time, which is set theory is what they were working with, anything derivable in set theory is derivable in the system of combinators. That's a really big claim. So let's see what he does with it. In Section C, those theorems deal with the equivalence of combinators after they're reduced. So, an example of reduction is, if you've got WBKCW, you apply a rule and it gets a little smaller, and you apply a rule and it gets a little smaller, and then you can't apply any more rules. So that's reduction. It's just, stepping through the rules until you stop. And sometimes you don't stop. You can build BCKW sequences that grow infinitely, which is a bit scary. It also Section C also deals with the idea of normal combinations, which I don't have time to get into, sequences of variables called groupings, and combinations with no parentheses that he calls transformations. And Section D is where it gets very hard, in my opinion. Curry uses the theorems from those previous sections to prove that combinators can represent a theorem of commutativity. And commutativity just means A plus B equals B plus A. You can switch the arguments, and the value doesn't change. So he's saying the combinators can represent a theorem of commutativity. So that's even one step further than proving commutativity of anything. And the following theorems and the ones in section E prove more concepts about regularity and the behavior between sequences of regular combinations. And that's the end. Hang on a second. Curry just said that anything we could write in ordinary logic can be written with combinators, but he didn't prove it. He just wrote a bunch of proofs about how the combinators behaved. And when I got to the end of the thesis, I was frustrated. I was expecting a nice proof of generality or Turing completeness or anything like that. And I went to go ask Dr. Hamlin about it because he knows about these things. And I'll paraphrase what he told me. So place yourself in the shoes of those early 20th century mathematicians. Set theory, which was the big main tool at the time to prove things, was proposed by Georg Cantor in 1874. And in 1900, it was proven to be inconsistent due to Russell's paradox. So that means that set theory as it existed in 1900, described by Georg Cantor, had paradoxes in it. Russell's paradox was inside of set theory, and that meant that it just wasn't right. It wasn't the right theory. It wasn't consistent. You couldn't trust it to do proofs because who's to say that your proof is correct if there are inconsistencies in the formal groundwork that you're building on top of. And so in those 26 years, there was no proof that set theory was complete or decidable or anything like that. The entire thing was built on hopes and dreams and duct tape. And the idea of classifying a model of computation as complete or consistent or decidable, like I said, was postulated by Hilbert in 1900, but it really wasn't even formally proposed until 1936. And I encourage you to read about the Church-Turing thesis, which dealt with the equivalence of the lambda calculus and Turing machines and what they could compute. Just to explain something, Hilbert, Curry, Church, Turing, they were all working together. They knew each other. They talked to each other for a long portion of time. They all, I think, all or most of them worked at UPenn together. So they all knew what was going on in each other's frameworks. So Church-Turing thesis, they worked together to figure that out. And so I hope you'll just trust me when I say that BCKW is Turing complete. It's Turing complete because SKI combinator calculus, which is it's an intersection of BCKW. So it's got that K is the same and the I is the identity function, but we can represent that as BCC. And S has a representation in BCKW. So they're really the same thing because you can represent each other, you can represent each framework in each other's terms. So there's a proof that SKI is Turing complete because it's equivalent to lambda calculus. And according to the Church-Turing thesis, lambda calculus is Turing complete. So you can take my word that lambda calculus is Turing complete, or you can read Turing's proof of it, which I've linked in the slides. And yeah, so that's the formal groundwork that we've got. Excuse me. But why don't we actually put the combinators to use? Why don't we represent something that we can at least get a grasp on? And so here is an encoding of church numerals. If you're not familiar, church numerals are a way to represent the natural numbers, which is 0, 1, 2, 3, 4, 5 to infinity. It's a way to represent the church, the natural numbers in a functional language way, basically. And so, down here we see that whatever we have for 0, it's a function. And it takes in an f, and it takes in an x, and it spits out x. So